Hi, Physics Tube. Mr. Janowski here. This is chapters 15 and 16, homework 3, and I think I'll try to do problems 4A and 5A here. Parts B and C of both of these problems are just the same thing, just with different numbers for more practice. So I'll try to do these things. So 4A, a proton has a rest mass of m naught is equal to 938.3 MeVs per c squared, which you can also say is 938.3 times 10 to the 6 EVs per c squared. So in units of MeV, what is the total energy of a proton traveling at, part A, 90% the speed of light? Okay, so we will start off with step, So what are we actually looking for? What is the total energy in units of MeV? So what we want is E is equal to question mark something MeV. Okay, so we will start off with, let me get the right color pen here. Our formula for total energy. Our formula for total energy is not sigma. My bad. Our formula for total energy is E is equal to m naught c squared over the ugliness term, 1 minus v squared over c squared. And in this situation, we know v. So as usual, when you know v, what you want to do is take just this ugliness term here. Beep. This guy over here. I could have circled that better. That's much better. This guy, take it over to the side and turn that into a number. So the square root of 1 minus v squared over c squared is equal to the square root of 1 minus, v is 90.0% the speed of light. So 0.900 c squared. So that there is v squared over c squared. So that's going to give us 1 minus, let me get the numbers in front of me. Well, it's going to be 1 minus 0.810 c squared over c squared. So I'm going to skip a step and just not write that. 0.810 and then c squared over c squared. They just cancel. So we have this. So again, when you're doing these, do your algebra very carefully. Take it one step at a time. So the square root of 1 minus 0.810 is going to be the square root of 0.190. So I ask the calculator, what's that number? And the calculator will tell you, I didn't mean to write the square root there. The calculator will tell you that this number is 0.43589. Such a lovely 8 and such a hideous 5. Okay, so we have that. So yeah, again, that means our ugliness term is this. 1 minus v squared over c squared. So we can take this idea, take it back over to here, and what that gives us is E is equal to m naught c squared over, the number we just found, 0.43589, which means E is equal to, and remember m naught is 938.3 MeVs over c squared. So that, what I've just written, is this, m naught. And look, this gets multiplied by c squared. And all of this over 0.43589. So the reason when you're doing these particle physics problems, you use these funny units instead of kilograms and meters per second and things like that. So yeah, you use MeVs per c squared for units of mass, is because right away, this per c squared multiplied by c squared, well, this is just going to cancel. So what you're going to get is E is equal to 938.3 MeV all of this over 0.43589. So you ask the calculator for that number, and the calculator should give you a number that, if you're keeping 3 sig figs, ends up being 2150 MeV. So 2150 MeV. You could also write 2.150 GeV, but typically when you're doing these, you want to keep it in MeVs. So put a box around it so that your physics teacher knows this is your final answer. And does this make sense? Well, we solved for the right thing. We solved for total energy in units of MeV. So, yeah, you're not going to have much practical experience in your real life. That E looks like a C. Okay, now it looks like an E. Yeah, you're not going to have much experience in real life comparing this to something you're used to dealing with. There's no like bloody cheetah rule for doing this stuff. But we did solve for the right thing. We gave it the right units. And that's a sensible answer. So we're happy about that. So jumping ahead to problem 5A. So yes, the SLAC, the Stanford Linear Accelerator Collider. I think that's what it stands for. Oh, Stanford Linear Accelerator Center. I was trying to remember. I had written it down already. Okay, it's right there. So they're going to accelerate electrons instead of protons. So electrons, this is why we use MeVs per c squared, and try to be consistent with that. You don't want to keep jumping back and forth from MeVs per c squared to GeVs per c squared. Yeah, notice this 0.511 MeVs per c squared versus for the proton, 938.3 MeVs per c squared. So that's why we do that. But anyhow, to what velocity must an electron be accelerated so that its mass is? So the thing we're looking for is the velocity. So what are we solving for? We want velocity, and we don't want it in meters per second. We want it to be some number times c. So those will be our units. So yes, so to what velocity must an electron be accelerated so that its mass is 1.1 times greater than its rest mass? So we're going to use the relativistic mass equation, which is m, so that's the observed mass, is equal to m naught over the ugliness term, 1 minus v squared over c squared. All right, and the thing we're trying to solve for here is v. So we've got to do some algebra, multiply both sides by the ugliness term, and that would give you, I'll do this slowly, m times the square root of 1 minus v squared over c squared is equal to, on the right-hand side, we have m naught. So go a little bit further, divide both sides by m, and you're going to get, oh, sorry, already I'm making a mistake. You're going to get, on the left side, 1 minus v squared over c squared is equal to m naught over m. Now, here's the thing. I did give you the mass of the electron right here, 0.511 MeVs over c squared. You don't actually need that. The thing we're trying to find is when is the observed mass 1.1 times greater than the rest mass? So let's just do it this way. On the top, m naught, and on the bottom, we want the observed mass to be 1.1 times the rest mass. So these just cancel, and this is equal to 1 over 1.1. And 1 over 1.1, let me get to the page. 1 over 1.1, I didn't actually write it out, silly me, is equal to 0.90909, which you can just write as 0.90 repeating is, probably the best way to write this. So yeah, at this point, 1 minus v squared over c squared is equal to this. Okay, so yeah, the thing I'm trying to point out is I didn't actually need this information. I could have plugged it in. It wouldn't have hurt. But it would have been in the numerator and the denominator. It would have just disappeared. It would have just canceled itself out. So I didn't actually need that. So what do we do from here? We're trying to get to v, so I'm going to square both sides. So on the left side, that's going to give me 1 minus v squared over c squared. And if I square that thing on the right, I get, sorry for the stray mark, I get 0.826446. Let's just keep a bunch of numbers for now. Okay, so I'm still trying to get to v. So what I'm going to do is subtract this number from both sides. So on the left, 1 minus 0.826446. I'm going to add v squared over c squared to the right. So that gives me v squared over c squared. So on the left, I'm going to end up with 0.1735537. And all of this is equal to v squared over c squared. So common mistake is, your calculator just gave you a nice number. It seems believable, but we're not done because this would be v squared in terms of c squared. You need to take the square root of this again. So yeah, very common in these problems. So let's raise this to the 1/2 power. And what we're going to end up with is that v is equal to 0.41659779. So let's just call it 98 right there. Okay, so we have that times c, which if we're keeping 3 sig figs, this will round off to be 0.41. That rounds up to 7 times c. So now we have a velocity in terms of c. We put a box around it. We do our step. We were looking for velocity equals to some number times c, and that's what we found. Is this reasonable? Well, it's greater than 0 and it's less than 1, which means our particle is not going faster than the speed of light. So yes, it is reasonable. So we give it a check. So that's how you do these kinds of problems, dealing with relativistic mass and total energy, things like that. And hopefully you found this useful.